Hi, and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about dimensional analysis. This is a continuation of my previous video in which I just introduced dimensions and units. So dimensional analysis is sometimes also called unit analysis. It's a nice tool for use in a few things here. You can kind of guess at what the basic form of an equation might be using dimensional analysis. It also can be a strong form of double checking your work on certain kinds of physics problems. If you end up with the wrong kind of dimension at the end of a problem, then you've probably gone wrong somewhere. Getting the right dimension doesn't necessarily mean that you've gone right everywhere, but it does mean that you haven't gone wrong in one of these sort of easy to find manners. So what is dimensional analysis and how does it work? Well, from the last video that I made, you may recall that the act of making a measurement in physics, quantitative measurement, basically means comparing the thing you're measuring to some standard of measurement. That is, you're comparing it to the basic unit of measurement. So if I measure a length and I say this thing has a length of 12 inches, I'm making a comparison to the standard unit of the inch. And so I'm saying that this is 12 times that standard length. If I say that it has a mass of 300 kilograms, then I'm saying that it has the same mass as 300 of my standard of measurement, the kilogram. Okay. A second thing to recall from that video, and this was not a point that was hammered there, but it kind of was in the background and it's worth bringing up now. There's two basic types of dimension and thus of unit. And I'm not here referring to we have two systems of units. There's actually multiple systems of units, the main one of which was the SI system within the metric system, specifically the MKS base. But the two types of unit that I'm referring to here are base units and derived units. So what are these two things? The base units are sort of the units that you are defining to be the basis for your system. So for example, we had meters and we had kilograms as base units. That means that length is a base quantity and mass is a base quantity. Time is a base quantity. Derived quantities come from basically some combination of these base quantities. All right, so these are the two main things to recall from that other lecture. And of course, maybe like, what are the base units? About the only thing on this list that we sometimes treat as not being a base unit for the purpose of an introductory physics course is that in Physics 2, we sometimes prefer charge as opposed to current. But that's neither here nor there. We won't really be using that much in Physics 1 anyway. So where's dimensional analysis come in? Well, the idea of dimensional analysis comes from the fact that units in an equation or an expression need to be consistent. What this basically means is if I have an equation that allows me to predict, let's say, how far an object has traveled. So on the left side of the equation, maybe I happen to have a distance or distance traveled. Let's say that maybe that's an x. If the equation says x equals, let's say, half of some quantity times some other quantity squared plus yet another quantity times maybe the same quantity here, then this quantity right here, this total term, and this right here, and this right here all must have the same dimension. Thus, if my delta x is a distance, then whatever dimension this has and whatever dimension this has, they need to multiply out to be distance. Put differently, if this has units of meters, then the units of this term and the units of this term need to multiply to be meters. So if this is a speed and I'm told that it's in meters per second, and this is a time and that's in seconds, then I would have meters per second times seconds, and that does in fact give me meters. The basic math works out over here. Do meters equal meter per second times seconds? Well, the seconds can cancel just like any other quantity that you find in both a numerator and a denominator of a fraction. This ultimately means you have a fraction. The seconds can cancel and you're left with meters equals meters, and so this is dimensionally consistent. Okay, we could do the same process with the 1/2 AT squared term. Maybe there's other terms, like you might have a term like this, JT cubed. But since we've established that time t is in seconds and x is in meters, that means that we now know what the units of the a and the j have to represent. So we'll make this sort of our first little example in this video. So given that we know now what t and delta x and v initial have as their units, what is it that j and a initial must have as their units to be dimensionally correct? Okay, first things first, when you have fractions or coefficients that are just a number out front, they often don't have a unit associated with them. So we can kind of like ignore the 1/6 and the 1/2 here. Now this is one of the limitations of this method, because if you try to reverse engineer this equation without knowing what the coefficients are supposed to be, you might be able to get, knowing the units for everything, that x should look like j times t to the cubed and a times t squared and v initial times time, but you don't know what to put in front, like a 1/6 or a 1/2 or a 1 or a -1 if it's subtracted. So this is one of the limitations of dimensional analysis. Okay, let's look at each of these in turn. So I have that delta x is equal to, or has the same units as, 1/6 jt cubed as far as dimensions are concerned. I'm going to use this little bracket around them to represent this is dimensionally consistent, whether the equation is otherwise true. It's obviously missing these pieces. Okay, this would imply that j has the same dimensions as 6 delta x over t cubed. And, we can kind of get rid of the 6 if we'd like. Okay, this means that the dimensions of j, which I'm just going to represent as the box around j, has to be equal to meters divided by seconds cubed. We've actually solved the problem at this point. We're done. Well, we have to do the other half, which is, what about this other term? Okay, so delta x is 1/2 of a initial times time squared dimensionally. And that means that a initial is 2 delta x over time squared. And again, we can kind of scribble out the 2 because it doesn't contribute any dimensions here. That means that a initial has to have dimension of x, or units of x, so that would be meters, divided by units of time squared, so that is seconds squared. And that's really all there is to using it in this way. So there are some kind of tips, tricks, and things to know about and understand with dimensional analysis. The first one, of course, is just this idea that any sort of quantity within your equation or expression has to be dimensionally consistent with the other quantities. So how do you know if it's a different quantity? Well, if it's separated by a plus or a minus, then it counts as a different quantity. Alright, so what are the basic rules for engagement with these? Well, any quantity separated by a plus sign or a minus sign should be dimensionally consistent with each other. So going back to our equation here, I've basically underlined each of the quantities that taken as a whole must be dimensionally consistent. Notice that the equal sign could fall into this rule. I've separated it as a second rule saying sides of an equation must be dimensionally consistent. So if you want, you could say, like, in some sense, this must be dimensionally consistent with this. That's equivalent though, because you can always subtract delta x from both sides of the equation, and now you're back to this and this have to be dimensionally equal. 0 as a quantity, when you have 0 times anything, you get 0, and so the dimensions of 0 are whatever you need them to be. Notice that quantities that are multiplied by each other or divided by each other are not within that multiplication or division necessarily dimensionally consistent. So this a initial and this times squared term, they don't have to have the same dimension as each other. It's just that whatever dimensions they have collectively as a quantity have to work out to be meters. Okay, so that goes with plus and minus sign are separators. Divided by or times are not quantity separators in this sense. Okay, some other stuff. Arguments of certain functions have to follow certain rules. Trig functions end up with units of radians or degrees, but we usually just say radians. Radian is kind of a placeholder unit. So if I have a quantity sine of k times delta x, and we know that delta x is in meters, then k, whatever it is, should have units of radians per meter, which we can sometimes just represent as inverse meters. So it's okay if we just say, like, there's no dimension to this thing inside the argument of the sine function, but it is in units of radians. Arguments of logarithms and exponents are dimensionless. So if I have e to the omega t, we know that time is in seconds, then omega has to be per second in order for this to be dimensionless. These two rules are kind of similar to each other for what it's worth. And when we say logarithms and exponents, that could include not just e to the some power, but any number to some power. So if I have 2 to the little t over big T, and I know that little t has units of seconds, then big T is also in units of seconds. Okay, so these are the basic rules of engagement. I've also noted that you can have coefficients that are dimensionless, that are positive or negative or even imaginary, that are thrown in front of a quantity, and that doesn't change the dimension of the quantity. So that maybe could fit into these rules as well. If you follow these rules, though, then your equations will tend to be dimensionally consistent, and this can be used as a good double check of that you've done something right, or as a way of guessing at what quantities are within an equation. Going back to our previous example, the AI here, a sub I, was meters per second squared. We know that meters per second is a speed, so this could be written, for example, as meters per second per second. Typically, anything per second is meaning something like a rate change of that thing. So this could conceivably be a rate change of speed. That's all for today. Thanks for watching.